we created the basic inverse trig functions and drew those. What about variations on that? So like when we're not so much the shifting on this one, but the dilations, things like that. So if I had to draw something like this, 5 times the inverse sine of x on 3. I think the trick with these is just to first of all work out the domain and range. I know that normally it goes in between -1 and 1. So instead of x going in between -1 and 1, x on 3 is going in between -1 and 1. I just play around with that inequality, multiply by 3, I've now got the domain for this function. I could do a similar thing with the range, but remember the range is grouped with the y, so that coefficient 5, I go to the other side, so it's y over 5. Inverse sine, that would normally go in between -pi on 2 and pi on 2. So then multiply both sides by 5, I've got the range. Now if it's the only graph that we're drawing, then I can pretty much draw the same graph every single time. I just change the numbers on the axis. So it's identical to the one I drew the other day, but I've now got -3 and 3 on the x-axis instead of -1 and 1. And I've got -5 pi on 2 and 5 pi on 2 instead of -pi on 2 and pi on 2, and then I just draw the basic inverse sine graph in, and there's a picture. This one's a little bit different, because inverse tan, well normally the domain would be all real x, you could substitute anything in. But if you have a look at what we're substituting in, that in itself has its own problem, because you've got a square root sign. And we know whatever's under the square root sign has to be positive. So that's going to control the domain. So 3 minus x squared has got to be greater than or equal to 0, which means x must go between -√3 and √3. Now when we had a restricted domain like this, what we did, we said, well, let's have a look, see what the endpoints are doing. And a lot of these things are symmetric. This one certainly is because of the x squared. Let's see what's happening in the middle. Now let's work it out. When x is the square root of 3, I get the inverse tan of 0, which is 0. I suppose I don't really need to do minus the square root of 3 because I'm squaring, of course it's going to give me the same answer. And in the middle, I'll get the inverse tan of √3, which is pi on 3. There's a pretty good chance that the range is going in between 0 and pi on 3. That usually captures it all, especially in these symmetric looking ones. But if you're unsure, you can test a few other points and just confirm that. Right. So let's draw it up. So on my x-axis, I'm going from -√3 to √3. The y-axis I'm going 0 to pi on 3. This graph ends up looking like, it's not actually a semicircle, but it's sort of got that shape to it. So it actually looks nothing like an inverse tan graph when you think about it. It's just this shape. Again, if you're unsure, plot a few more points and then the shape will start emerging. This sort of one, the inverse sine of sine x. Temptation is to just draw the line y equals x because inverse sine and sine will cancel out. But we have some issues. So let's do it the same way. So domain, well normally it goes in between -1 and 1. So for our one, sine x has to go in between -1 and 1. So when does sine x go in between -1 and 1? Well, it always does. So alright, I can actually substitute anything I like into this and I'll get an answer. But the range, it is still an inverse sine function. So it's going to have the range of an inverse sine function. So -pi on 2 to pi on 2. So it's not simply going to be the line y equals x. Let's just draw this up. Plot a few points in. Essentially, it's y equals x, but I've only drawn a piece in it, you see. Because I know it stops at -pi on 2 and pi on 2. So there's y equals x. But the domain is all real x. So what does it do after these things? Again, you could just test some points to find out. But what actually ends up happening is we end up with this zigzag. Check the key points. Pi, you get 0. Then the next one here would be 3 pi on 2, sub it in, you get -pi on 2. And then the zigzag would emerge. So on this one, the zigzag goes in both directions. What about the other way around if I said the sine of the inverse sine of x? So now it's a sine curve, but again, it should be y equals x. What's going to happen here? Domain. Well, now I'm actually substituting into the inverse sine function. And that has its restrictions on the domain. So I can only substitute x values in between -1 and 1 for this one. The range. Well, let's test those endpoints. I've got a restricted domain. Let's see what happens. When x equals 1, y ends up equaling 1. Kind of expected that because it's based on y equals x. -1, yes, I get -1. In the middle, 0, I get 0. So alright, it is -1 to 1. Draw this one up. Y equals x, but that's it. This one just stops. It doesn't zigzag because the domain is going from -1 to 1. So these ones you've got to be real careful with, well, which ones are just going to stop and which ones will keep going on. And I guess it's all controlled about what you're substituting in initially. The first one I was substituting into the sine function, and the sine function is all real x, so it'll keep going. Whereas this one I'm substituting into inverse sine of x, and well, that only works in between -1 and 1. So I stopped there. But once again, if you're ever in doubt, just pick a few numbers, substitute in, see what happens. Do you get an answer? Does the calculator come back with an error so you know, actually, no, I can't plot that point? So 17C will draw up some inverse trig graphs.